Today we're going to review the Minerals Lab. I'm going to provide you an overview on some of the more key points to help you work through the lab, improve your comprehension, and also make the lab run more efficiently. I'm not going to reiterate everything you learned in lecture. We're just going to go over some of the main points that we covered in lecture that are relevant to this lab. And then I will spend the second half of this review looking at the hand samples to show you how you actually go about looking at some of the diagnostic properties and how you'll use a mineral key to identify the minerals. Now, if you remember in lecture, we talked about minerals having five components that we use to define them. The first was that minerals have a specific chemical composition, that all minerals have unique compositions that are reflective of a given mineral. For instance, this material here, this quartz, is comprised of silicon and oxygen, and it has a ratio of one silicon atom, in this case here, overall to two oxygens. And that is its chemical composition. But that by itself is not enough to identify a mineral. Clearly, some minerals have the same chemical compositions, but they can have very different properties. And that's because their atoms can be arranged in a different manner. And so the second important factor is the atomic arrangement, how the atoms are arranged. And I'll show you an example of that shortly. The third point, minerals are all solids, and that's by definition. You can't have a specific atomic arrangement or a crystal structure if it's not a solid. So by definition, the native element gold is a mineral because it's solid at room temperature. The native element mercury, which is liquid at room temperature, is not a mineral, even though they're both native elements. Fourth, minerals are inorganic. Materials or substances that form from biogenic processes or life processes, by definition, are not described as minerals. So you can have the mineral or the chemical composition of calcium carbonate be produced biogenically in a clam shell, and that's not a mineral. But you can also have calcium carbonate directly precipitate out of ocean waters, and it is a mineral when you find it in the inorganic limestone. So inorganic only. Number 5, minerals are naturally occurring. And by naturally occurring, meaning they cannot be produced in the lab. Now, if your significant other buys you a cubic zirconium ring for your engagement, you have every right to say, honey, I like your thought, but that is not a real mineral, and I would like you to buy me a diamond. Now, if we look at this idea of chemical composition, why it's by itself cannot identify a mineral, we can look at graphite and diamond. Both graphite and diamond are formed of pure carbon. The difference being is graphite is defined by carbon sheets. And you can see here that when we look at graphite, you can see that it is made up of sheets of carbon with 3 bonds here. These are strong covalent bonds for the 3 atoms that we see here connected. And you can see these connections go throughout the sheets. And these sheets are very strong within the sheet, but you have these really weak van der Waals bonds separating the sheets. And so graphite is a very weak or soft mineral. And it's the mineral you find in pencil lead. And when you write on a piece of paper, what happens there, the pressure on the graphite, as you write on the paper, it flakes off into sheets because of those weak van der Waals bonds. Now, diamond, on the other hand, is also formed of pure carbon, but it has a very different structure. It has a more compact structure. Diamonds form really deep beneath the surface of the earth under very high pressures. And so the carbon atoms are very compact. The bonds between the carbon atoms, there's 4 of them there, are all covalent. And these are very strong bonds. Okay, strong. As you know, my handwriting is terrible, but that does say strong. And with this, diamond has a hardness that is harder than any other naturally occurring mineral on the surface of the earth. And it has to do with atomic arrangement and the bond strength. Now, the other point that we came up with is this idea about crystal form, that these minerals have atoms arranged in certain manners, and you have a crystal that forms because of it. In this case here, we have quartz is a 6-sided pyramid-shaped crystal. You can see it right here, and you can count the sides, 3 on this side and the 3 on the back side of this PowerPoint slide. Now, you'll note here that we don't always see the crystal form of a mineral in a rock. And that's important because you're going to be looking at a bunch of rock samples this quarter, and you're going to say, Terry, where's the six-sided quartz crystals? I don't see them there. And that can be for a range of different minerals. The simple rule of thumb to note here is that minerals will have a crystal form when they form in an unrestricted environment. What that means is that you don't have other minerals around them crowding them. Now, a case in point, you can look at the rock granite. Granite has, in this case here, 4 different minerals present. You're going to learn all these in lab today. The one mineral that I actually identify here is the quartz. And quartz is shown here. It's this glassy gray mineral that's shown here. You'll note that you don't see any 6-sided pyramid-shaped crystals here. Now, the interesting thing about quartz is quartz forms in this granite has a very low melting temperature. Quartz is the last mineral to crystallize. All the other minerals that you find in this granite crystallize first. So what that means is that they get formed and they can have their unique form manifested. It's like going to a concert, getting yourself set up, you got your blanket all laid out, you get there first, you spread out, you have all that room, you get to be yourself. You're one of the late arrivers, you get pushed down into the crowded area, you like body space, but you're cramped in between all these people, and you don't manifest your true form. Quartz is the same way. Low melting temperature, last to crystallize, has to fill in the void spaces. You don't see its crystal form. Very important thing to remember. Now the question is, where do minerals form? Now, minerals form naturally in 2 different locations on the surface of the Earth, or near the surface of the Earth. Minerals can form from magmatic melts, from molten rock. And in the case here, you can see a lava fountain. This is a basaltic eruption on the Big Island of Hawaii. When that lava gets erupted, it crystallizes, and the minerals directly crystallize out from the magmatic melt. Now, an important point to note that we mentioned in laboratory is that the rate of cooling has a very strong influence on the size of the mineral crystal. The faster the cooling rate, i.e., lava that's erupted to the surface of the Earth crystallizes very rapidly, you're going to have small crystals. Okay, when cooling rate is fast. Okay, and that is at the surface of the Earth. Okay. Now, on the other side of this, if you've got magma crystallizing deep beneath the surface of the Earth, or beneath the surface of the Earth, it's going to crystallize slowly. The cooling rate is slow. And what that means is you have plenty of time for big crystals to develop. And so these big crystals will form as it cools slowly underground. So case in point here, magmas that crystallize or molten rock that crystallize underground, you're going to have bigger crystals. Okay, big crystals. Okay, sorry you can't read that. That's okay. Okay, and that is underground. And what's neat about this rock is it actually has 2 crystal sizes. You have big ones here, these white crystals, but then you have this matrix or this fine-grained area here that you can't see the crystals with your naked eye. And what that tells us is that this rock actually had 2 stages of cooling. It started out as magma underground. The big crystals crystallized first underground, then it got erupted to the surface, and then the matrix crystallized very rapidly and forming these very fine crystals. Now, let's actually look at what you're going to learn in the lab and what are some of the physical properties you're going to look at here. Here is our friend quartz again. In this case here, we have a number of these 6-sided pyramidal-shaped quartz crystals growing out. In this case here, in an unrestricted environment here. Now, clearly, crystal form is only one of the features. Quartz has a lot of diagnostic properties that are representative of identifying as quartz. It's a very hard mineral. We're going to learn later that it doesn't have weakness planes, it fractures. There's a whole range of things that we can look at, and I'll show you these with some of the specimens there. But when you actually get to the laboratory, you're going to see a tray full of 14 minerals. You're going to say, oh my God, how am I going to learn all these? But it's really easy. What we're going to have you do is there's going to be about 4 or 5 diagnostic properties. You're not going to learn all the diagnostic properties. You'll learn 4 or 5 of the common ones we use. And then at the back of the lab manual, we have an appendice with some of the mineral identification charts. There are 3 charts there, and these are flow charts. And what you're going to learn is we sort of have these charts subdivided into some of the main classification schemes that we use to subdivide minerals. Okay, and I'll show you what those are. Okay, when I actually show you with the hand specimens. But the first thing to note here is when we're actually looking at some of the common physical properties of minerals, we look at luster. Okay, that's an optical property that when we're looking at how light shines on the mineral. We're going to look at color and streak, and I'll talk about that. Hardness, how hard the mineral is, which reflects the bond strength and the chemical composition. Cleavage, which are weakness planes, and fracture, some minerals do not have weakness planes, and the crystal form. So those are some of the main diagnostic properties that we're going to use to classify minerals. If you look here, you can see this is a quartz crystal. One thing, you can see the six-sided pyramidal shape. So that's one thing we know to identify quartz. Also shown here is luster. Quartz has a glassy or vitreous. Vitreous means glassy, luster to it. And so that's one of its properties. There's lots of minerals that have vitreous lusters in them. A lot of your gemstones, like emeralds and diamonds and sapphires, have a glassy or vitreous luster to them. And I'll show you some examples of other types of lusters with the hand specimens. We mentioned weakness planes or cleavage planes. Here is in this case here, a photograph of halite, okay, which is table salt, which you know is comprised of sodium chloride, NaCl. And note that table salt actually has 3 weakness planes. And the reason it has 3 weakness planes is because there are relatively the ionic bonds between the constituent sodium and chloride ions have sort of a preferred plane that repeats itself throughout the structure where it can break. And so you can see that sodium chloride or table salt, and we call the mineral, its name's halite. Okay, so you have 3 different terms we use for the same stuff. You'll note here that there are 3 weakness planes that form in this at 90 degrees to one another. And so you might say, well, hold it, Terry, how do you know that's not a crystal face or just a crystal face? And what you want to look for in the laboratory when you're studying cleavage planes versus crystal face is you want to see, does the plane repeat itself throughout the mineral structure? And you can see on this photograph here, you can see little stepwise sequences of this plane breaking off and repeating itself. And so I'll show you with a hand specimen how we can do this, because this is important, how you differentiate cleavage planes from crystal faces. The next property is hardness. And I showed you this slide in lecture, and it kind of makes you feel a little sick. Not everyone likes to go to the dentist. This is a dentist drill drilling into a tooth. The tooth is made up of apatite, okay, which is a mineral, and the drill bit has diamond bits on it. And what we discussed in lecture is that you would not want a dentist drill made of apatite drilling into an apatite tooth, because you'd be in there for hours. When you're looking at hardness, you're looking at bond strength. And diamonds, remember, have very strong covalent bonds. And so the harder the substance relative to the material that you're trying to scratch or abrade, the more easily you're going to be able to abrade it. So diamond is the hardest substance. Apatite is much softer, so the diamond drill can go through it quite rapidly. The final diagnostic property that I want to discuss here is streak tests. And this is most diagnostic for metallic minerals. And with a streak test, you're going to have a porcelain plate. You're going to take your metallic mineral. You're going to drag it along the porcelain plate, and it's going to leave a diagnostic streak. In many cases, the diagnostic streak is a property that is very indicative of a given mineral. And so in this case, this is hematite, and the streak is reddish brown. And you can see it right there. And that is always diagnostic of hematite. So now what I like to do is, for the last part of this lecture, is I want to go over some of these properties and show you some of the hand specimens, things you're going to see in the laboratory. Now, I brought a few minerals you won't see just because they're kind of cool. We can't do all of them, but I do want to use these to illustrate and not give away all the minerals ahead of time of what you'll be studying in your laboratory. Now, the first thing I mentioned was luster. Now, when we're looking at luster, we can separate minerals into metallic minerals, such as this is iron pyrite. And many of you are very familiar with metallic lusters. They sort of have that shiny look to them, like quarters and nickels, and a lot of your metals, gold and silver, Okay, these metals, they have certain properties, metals. And one of them is, of course, the metallic luster that's reflective in this manner. And then the second major subdivision of luster are the non-metallic minerals. And that is all of the other minerals you're going to discuss today. So you have metallic and non-metallic lusters. Okay, and you can see here, this happens to be a vitreous or glassy luster. So I'm going to put the metallic one down and show you some of the other non-metallic lusters. Now, this one is glassy, and this is a piece of sphalerite. I can give you its name because we're not going to have it in the lab. But sphalerite has a resinous luster. And you'll note it looks a lot like dried resin. You can see it here, okay, right beside this vitreous or glassy luster. And so you're going to get to see these different properties. Your TAs will show you, and they can help you, okay, and you're going to get familiar with these lusters. A lot of them will be glassy, okay, and then, of course, we'll have some of these other lusters that you'll learn in the laboratory. Now, there were some other properties that we need to look at that are important for identifying minerals. One is hardness. One thing that we do to separate minerals in the laboratory is you'll note that we have your mineral keys at the back in the appendices. We separate the metallic minerals first, and then we have all the keys for the metallics, which are easy to identify in their luster. Then you can use, with the metallic minerals, we can use a streak plate. And so in this case here, I talked about hematite in the PowerPoint slides. I'm going to show you here. I've got a piece of hematite. I'm not going to show you what number it is in the mineral tray, but I'm going to streak the porcelain plate. And you'll note that it makes a nice sort of reddish brown streak. And that is diagnostic of hematite. It always is. But you'll have a few other metallic minerals that you'll be looking at in the laboratory, and you can streak them, and you can see that they'll leave diagnostic streaks which are defined or described in your metallic mineral flow chart. Now, there are some minerals that, they don't really streak. You can take this mineral and go to streak it, and you'll see there's this white streak, but you need to be careful. The mineral may be so hard that it's actually causing the porcelain plate to flake off there. So, as I said, you can streak some of the other minerals. If you've got a light-colored mineral, you may want to use the dark streak plate, okay, to leave a streak on it. And again, remember that streak is not so characteristic or diagnostic of the non-metallic minerals. Now, one thing that we use a lot is the hardness test. Now, we're going to learn that minerals have different hardnesses. We have a scale that we rank for mineral hardness. It's called the Mohs scale, 1 through 10. Okay, I'm not going to go over it now. Just to remind you, it's not a linear scale. It's ranked 1 through 10. A mineral like diamond, which has a hardness of 10, is not 10 times harder than talc. It's thousands of times harder. So just think it's a relative scale. But one of the features that we look at here when we're trying to classify minerals is we ask, is it harder than glass or softer than glass? That's one of the first things that we can do. So I'm going to show you two minerals. When you're actually doing the glass test, make sure you put enough pressure on it. So here I got this glassy mineral again. I'm going to take the glass plate and I'm going to put some pressure on it. And then what I do to make sure that the mineral's scratched is I'm going to rub my finger on it. Because sometimes a mineral can appear to scratch, but it's actually the mineral breaking off onto the glass. In this case here, you can see that this mineral was harder than glass. It left a scratch. Here's another mineral I have that is not as hard as glass. Okay, and you're going to see this. I'm going to go to scratch it. Note here. Okay, maybe that left something there, but I'll take my finger and it rubs off. This mineral is softer than glass. And so what you'll do with all your 14 minerals is you'll go through, are they harder than glass, softer than glass? And then the other thing we have here, and I'm not going to demonstrate this right now, is we have a series of these hardness probes. And so these hardness probes, you'll note that they have numbers on them. This probe has a hardness of 6. So if this probe is scratching a mineral with a hardness less than 6, it'll scratch it. If it's got a mineral harder than 6, it won't scratch it. And so you can use these probes to kind of fill in the blanks when you're trying to get a better, closer, understanding or representation of the hardness of a mineral, which is very diagnostic of trying to identify it. Now, the other important point, so we looked at hardness, we looked at luster, we looked at streak test. The last thing I want to talk about today, as far as major properties, is the cleavage planes. Okay? Now, the cleavage planes, if you look here, this is a mineral that has cleavage. And you can see it as it's reflecting light, in the lab room here. You can see it reflecting. Now note this mineral, you can say, well, hold it, Terry, how do you know that's not just a crystal face? The first thing to note here, if you look at this as we pan in on this closely, you'll note that this face breaks off into steps. And you can see these steps continually repeat itself throughout the entire crystal. And so that's the first dead giveaway that's not just a crystal face, because it's breaking off continually throughout the mineral along this same face. And you can turn it over and note that this mineral, there are other cleavage planes. This mineral here actually has 3 cleavage planes, not at 90 degrees. Okay, and you can see not at 90. You'll learn it. The main point I want to get across here is the difference between a cleavage plane and a crystal face. Okay, the cleavage plane repeats itself throughout. Now, if you note, we bring our old friend up here. I've been showing you this guy a lot because you'll see this mineral a lot. Note that it has this 6-sided pyramidal-shaped crystal. Okay, if you look at that. Okay, and you'll say, well, how do you know that's not cleavage planes? Well, turn the mineral over where it's been broken. And you'll see on the end there that those clean planar faces do not repeat throughout the mineral. This mineral breaks off along fractures. So this mineral does not have cleavage planes because the planes don't repeat throughout the structure of the mineral. Okay? Very important. The last thing I want to mention is a few other diagnostic properties that you will use, and they're often enough by themselves to identify the mineral. This mineral here, I'm not going to give you its number, is magnetic. And note the magnet sticks to it. That is the diagnostic property of that mineral. You can do the streak test with it. You can do the harder than glass test with it. And what you probably will, or maybe you don't have time, if you find out it's magnetic, you go to your flow chart. Okay, there's one mineral that's magnetic like this. You've identified it. Another mineral like that that's quite common, I'll take this one I showed you with the 3 cleavage planes, and you can drop hydrochloric acid on it. And this mineral, when you drop acid on it, you will note that it fizzes. It reacts with the acid, which is diagnostic in its own right to identify that mineral. Okay, so those are some of the main important points of the Minerals Lab. I want to stress, I know there are answer keys out there, right? We've discussed this at the beginning of the quarter. You guys signed an agreement at the beginning of lab that you know there are answer keys out there, but you made a solemn promise. You're coming into lab to learn. You're coming in here to not worry about that you learn all the minerals, but you're learning how science works. And the important keys to come away from this lab is how a dichotomous key works, how we can use physical properties of the minerals to identify them, and that's what we're really looking for here. Just do your best, enjoy yourself, and I will see you next week when we discuss igneous rocks. And good luck, and I will see you